So on this distributed hash table research side, I think there is a few kind of goals here. One is scalability. So we want to make it work with more nodes. We want to make it faster to respond to queries. But I think probably the most tricky problem is around security. So there's a few fundamental problems. One is well, okay. So what's our sort of threat model here? There's a few things an attacker can do in a DHT. They can try to control the nodes that are storing a certain records, like for particular blocks. If you wanted to block something, you basically get your address, your node ID in the right place in the identifier space so you can control that and you can give out bad data. You can instead try to not control that particular node, but you try to control all the nodes that connects to. So it's impossible to actually reach a particular node. So that's called an eclipse attack. And there's a sort of general approach to attacking a DHT is to make a whole bunch of different identities, and that's called a Sybil attack. And part of the fundamental problem with Sybil attacks is that there is not any complete fix. I mean, this is an impossibility result. Essentially, if you allow anyone to join the network and you don't have any sort of central authority who decides, you're allowed in, then there's no way to really know if two identities belong to the same attacker or not. So in some ways, it's more of a question of, well, what is it worth trying to protect against? What is it not worth trying to protect against? And what does that really look like? Yes, next. So I think the first thing to look at is, what should we really be doing that we're not right now? And there's a few of those things. So the original Kademlia is sort of by far the most widely used architecture for DHTs these days. There was a follow-up called S-Kademlia, and it proposed a number of things. One was making lookups follow multiple disjoint paths. And what that means is, in the current implementation, you're just looking for the closest ID, and you iterate trying to get closer and closer. But if one of those nodes that you talk to gives you fake results, then that are closer than anything that's really out in the network, then you're just permanently off the road and you're just going to fail. So any bad node in your lookup path causes a complete query failure. So the simple solution to at least make that somewhat better is you choose some finite number of different paths where you don't let any node be in more than one path, and you make these in parallel. So that's called disjoint paths. There's also concepts of wide paths where you sort of treat nodes as groups, and you say, well, I'm going to query this collection of nodes and then get the result from that collection and keep going. That's a very partial solution. The other thing that S-Kademlia proposes is a basic proof of work concept, which I'm actually not sure if anyone has really implemented this. We certainly haven't, and I'm not sure that it's worth doing because the DHT is kind of a low-level thing in the stack, and you don't want to require nodes to actually do a lot of work. So trying to protect against Sybil attacks by making things slower is really probably not the way we want to go. So that's not going to work. I think I'll skip Coral, but probably the most interesting idea in the last decade or so has been with around DHT security is taking as input a social trust graph. So there's this paper called Farnow, spelled WHANAU, that kind of originated this whole branch of research. And the core idea in Farnow is that you make random queries through the trust graph, and you're probably not going to cross a boundary between sort of a real set of nodes, and with high probability you're not going to veer off into a Sybil network that's all made of fake nodes. And to attack this, you need to create real social connections. The problem is this isn't really applicable to libp2p because we don't have a way of, that's a big requirement to say you need some sort of trust input. So I don't think that's really going to be workable. So the question is, what can we do? And what is worth trying to defend against and what isn't? Can we look at, the past behavior of nodes to predict the future? Perhaps. But that's very limited. It just makes it harder to do some sorts of attacks, but doesn't fix others. All right, I think that's about it. Questions? Yes.
Yeah, another completely different direction in predicting is just trying to detect attacks.
Yes.
And then, yeah.
Right. So then the question is, no, that's a great point. So you can try to detect attacks, and then there's the question of well, what do we try to do about it once you detect it?
Of course, but knowing is better than not knowing.
Right.
Like it's already like a tiny step in the right direction.
There's a bunch of papers around actual attacks that have been done on the BitTorrent mainline DHT. But yes. Other questions?
I think in general we should just, since there are certain impossibility results, say that we can defend against these attacks because that's the social cost of chip identities, but can we at least make it more expensive to conduct the attacks in the sense that a rational adversary wouldn't bother? So this doesn't have to be computational cost, it can be slow to conduct the attack. If it takes like 1 month to conduct the attack, no script kid is going to have the patience to do that.
I strongly agree. I think that's going to be probably the only practical way forward.
Make it more annoying.
Yes.
But not less possible.
Exactly.
Yeah.
Exactly.
Next.